on hybrid power systems from Mihai, Dorobantu. So thanks for coming, Mihai. Dr. Mihai is Director of Technology Planning and Government Affairs for the Eaton Vehicle Group and has been with the company since 2005. Prior to Eaton, he was a technology leader and member of the technical staff at United Technologies Research Center in the areas of modeling, analysis, controls, and embedded systems. And before, he was a member of the technical staff at COMSOL AB. Dr. Dorobantu has a PhD in applied mathematics from the Royal Institute of Technology and Stockholm University, Sweden. So, Mihai, thank you very much for coming again. Please go ahead with your presentation on hybrid power systems. Thank you.
Thank you for the introduction, and I want to thank the organizers for the opportunity to talk to you today. I'll talk a little bit about Eaton very briefly, just to give context to the meat and potatoes of this presentation, which is really to share our experience as well as the barriers and the opportunities that we see going forward with electrified powertrains in general. So very quickly, Eaton is actually a diversified industrial company. We are in the vehicle business. Vehicle business is about 20% of our business. We're much bigger in another piece that affects decarbonizing the economy, which is power distribution. We also have an aerospace and hydraulic business, and the reason this is important is because there's a lot of competencies from these fields, from the electrical systems, hydraulics, and aerospace, that we can actually bake into the vehicles, and it works the other way too. Our vehicle business is mostly focused around fuel efficiency, emissions, and maintaining performance while reducing emissions. So in the pass car land, we work with almost all engine manufacturers in the world. We have torque control products. We care about emissions other than the engine, for example, evaporative emissions from the fuel tank and so forth that have high GHG and NOx potential, GHG potential and high NOx. But in the heavy-duty world, again, we work on the engine side, on valves, valve strains, boosting mechanisms, and things like that. But what we're known for is transmissions of all kinds in the medium-duty and heavy-duty world. We've launched medium-duty dual-clutch transmission as an efficient power-shifting transmission. Recently, we have a big hybrid business. Used to be global, now it's mostly focused in China. We do a lot of other things, and through recent acquisitions, we are now also working in the switching and power conversion, electrical power conversion, up to and including ultracapacitors, which was news to me, but it actually works well with our portfolio. And we are the independent manufacturer. We tier one supplier. We work with everybody in Europe and in the world. So what I want to talk to you about today is how CO2 and NOx regulations are forcing technologies and why we believe the timing for that is 2024, and we don't think it's 2025 or 2023, but we think 2024 is actually a watershed year. Now, and for long haul, the immediate low-hanging fruit, if you wish, is really mild hybridization at 48 volts. And there's a lot of hype about Tesla and the Nikola and things like that. I spend a lot of time, every time there's a press release, the board picks up the phone and asks, when is this happening? What's going on? However, there are changes in the hybrid architecture that allow hybrids to be significantly more efficient and more flexible today to address some of the medium-duty needs, and especially buses and things like that. And the emerging player is really EV commercial vehicles, which for us are really important because they represent a very different way of using gearboxes, and it's an essential way for those vehicles to be successful. So, we talked, the speaker before me talked about the low-hanging fruits. And the low-hanging fruits are pre-technology forcing. And if you look at what the EPA CO2 rule does, it starts with a baseline, and that is a US baseline, roughly speaking, 32 liters per 100 kilometers for long-haul tractors. And it pushes it down by more than 25% over the span of 10 years from today, actually less than 10 years from today. So that means, essentially, it pushes the fuel consumption of such a truck at 26 liters per 100 kilometers. That's a pretty good number. On top of this, there's a trailer regulation with an additional 8% efficiency by reducing the load from the trailer. This is just the tractor side. So here's a challenge for the low-hanging fruit, and this is the effect of regulations. This is not business as usual. That is driving the U.S. engine and vehicle industry. And with that CO2 challenge, there is also an engine challenge, and we discussed the pros and the cons of having one standard or having a vehicle standard and an engine standard. The engine standard is not as tough. It only asks for about 6 to 7% improvement. It kind of sets a minimum improvement target on the engine. All OEMs realize that they have to squeeze more than 6% in terms of efficiency from the engine only in order to reach 25% on the full truck. By the way, for rigid trucks and medium-duty trucks and buses and stuff like that, the target's not 26%, it's about 21%. Still, it's a huge target. It's actually a harder target for non-long-haul trucks because those trucks do not have the benefit of the aerodynamics knob. You can't turn that. Now, on top of this, we have California Air Resource Board coming in with regulations, which today are voluntary, that are taking the NOx emissions down by up to 90%. There are actually 3 stages of it: 50% reduction, 80% reduction, 90% reduction. CARB is in the business of setting rules, not necessarily how to achieve them. So that's what they want. Voluntary today. Remains to be seen if the EPA will come in with a more moderate version of this or not. Who knows? But if the EPA does not do anything about this, then California will go its own way. I think that is pretty much the big stick that California has. And the way California goes, there are other 10 states that require CARB certification to drive trucks in their state. So that might be a U.S. de facto standard. And the timescales for the big changes for both of these things are happening in 2024. And that's not a lot of time for the industry to react, right? So, okay, ways to change the game big would be, for example, in long-haul battery electrical vehicles. I don't expect you to read this chart, but what it essentially says that if you want to do a long-haul tractor that has a modicum of performance, and, you know, like in Europe, 95 kilometers an hour. The US speed limit is even bigger than that, but let's call it 95 kilometers an hour, and be able to climb at that speed a 2% grade, which is hard for humans to even feel. You will feel it if you're power cycling, of course. Then that power request is about 400 horsepower, which is really, or would be with a very aerodynamic truck, which is why we have 400, 450 horsepower engines, diesel engines today on trucks. If you needed to do that electrically, and drive 400 kilometers, say, and then either do a fast charge or swap batteries or whatever, you would need storage in the tune of, half a gigawatt. And in the optimistic $150 per kilowatt hour cost, that's, $70K in batteries, almost $70K in batteries. Tesla, that we mentioned today, has offered this year, I think, to the government of Australia to take care of their blackouts. And they offered large-scale deployment of lithium-ion batteries in a stationary application, which is kind of where you use the vehicle batteries after they are no longer useful for vehicles. So in a much simpler application, at what turns out to be $600 per kilowatt hour. Of course, Elon Musk did not mention that number, but when you do the math, how much he was asking Australia to pay for how much installed power, that is a realistic figure today for a battery manufacturer to make money, a lot of money, out of batteries. So there's a big gap between 600 and 150. At $600 kilowatt hour, which is not out of whack with what I've heard earlier today, that 67K price quadruples, right? So I may be put to shame by Tesla's announcement that's now people are waiting for in September or October. We'll wait and see. But so far, the battery electric long-haul truck does not seem like a realistic opportunity. Now, we could do something better than that. For example, a serious hybrid, essentially like a locomotive. So you would have a diesel power plant operating at a single point so that you can really optimize, you can achieve that peak efficiency, and with all the progress that we can do, that peak efficiency might be 50%. Right? Brake-specific fuel consumption. But then with a pair of electrical motors, which would be in the 93% efficient range and so forth, you can work your way back, and from the actual demand of a truck, you would end up using, in an hour of driving, 9.4 gallons. Of gasoline, whereas if you go the other route, the conventional route, with a good engine, but within reach engine at 45% efficiency around sort of a broader area, and with a 98.5 efficient transmission, which is kind of at least the baseline for today, you would actually do better. Now, it is true that a serious hybrid, if you put enough battery in it, can then store some energy when you're going downhill and use it when you're going uphill, so you do have some of that energy storage and reuse effect. So at the end of the day, a serious hybrid on the highway would have marginal CO2 advantages, not if it goes on a straight road, right? Because then you have no hybrid advantage, but with sort of, if you have the right hills with the right length going down and right length going up at the right grade so that they perfectly match your batteries, you will get a slight advantage, but nothing out of this world. You can improve this with for example, a CNG-driven microturbine, fully recuperated, and things like that, or with hydrogen, as was discussed. But these are enormous infrastructure barriers that we have a hard time seeing coming. So probably the good old internal combustion engine, as highly optimized, good transmission behind it, it's still sort of the path to go forward, and it still would satisfy, the conventional powertrain will satisfy those pretty demanding, 25% reduction needs of US CO2 regulations. What does make sense, though, is to use more electricity on board. So we're looking at 48-volt solutions because that allows allows manufacturers really to to eliminate a lot of the losses. So certainly auxiliary losses, but also hotel losses. even by using a motor generator, permanent magnet motor generator, high efficiency electrical machine, just in the generation of electricity today on the truck, you can save a few kilowatts, and a few kilowatts means whatever it is, they're 1.5% just by the efficiency of the alternator today. The alternators are horribly inefficient today, but also magnificently inexpensive. Now you can use that electricity to do DEF preheating, as we've heard before, but you could also do creep mode, for example, which is a large source of NOx, so low-speed driving. You only need 15 kilowatts maybe to drive a loaded truck on not on a grade. So you could do that without an engine. And the nice part about it is the technology is there. It is today. So readiness is pretty high. If we look at hybrids, Eaton has had a hybrid business since 2007. So now it's our 10th anniversary. We have more than 12,000 commercial vehicle hybrid systems sold throughout the world. We sell about 1,000 systems a year in China, mostly in buses. In buses, our Chinese customers are seeing a 40% reduction in fuel burn, and they're given the fact that there is no NOx, no, that's not true. There's limited NOx after treatment and so forth. There's a double benefit of less fuel and less emissions. Now, some of that 40% actually comes because of the baseline. The baseline is a manual driver in a city, not particularly the best possible. The human is not the best possible controller for fuel-efficient powertrain. So there's an automation advantage that comes in that 40% number. But the value proposition just based on the cost of safe fuel is still a challenge, which is why these systems today essentially live in China, but not anywhere else. Everywhere else, it's onesies and twosies. On top of this, we had in around 2010 a huge challenge when CARB came back to us yelling, we are incentivizing hybrids in California, and we're seeing a 30–40% spike in NOx. So yeah, you may be saving us some fuel, but you are spewing out NOx. And oh, by the way, we didn't tell you, we wanted hybrids to reduce NOx, not to reduce fuel consumption, but just as a by the way. So the immediate culprit, suspected culprit was, the hybrid system turns off the engine cools down, turbine cools down, then after treatment system cools down, takes a lot to bring it up again. So we manage the controls, and you can see in the graphs on the right, you can see the SCR in and out temperatures in the conventional and in the hybrid system. And you cannot, sure, I could have plotted them on the same graph, but in the I norm, you cannot make a difference between them. We did fiddle the controls of the hybrid controls to talk to the after treatment controls so that we're essentially ensuring that we're maintaining the same temperature at the SCR. So we eliminated that source of NOx. Yet, if you look at the black curves, that's NOx piling up at a relatively slow rate in the conventional. That's an EPA 2010, so roughly speaking, a Euro 6 engine, and at a much higher rate in same engine in the hybrid situation. So again, lo and behold, what's going on? Well, what's going on was, this is what happens when you do hybridization without sort of doing the systems thinking. We had the same engine, now we had a hybrid system, so for a lot of the time, we're actually offsetting the load on the engine. So that engine in conventional case was run most of the time over the 75 kilowatt line, so pretty much in its best efficiency and low NOx. That's smack in the middle of NTE, so where NOx is strictly controlled. In the hybrid version, it's running light load. That difference in load is about the 40 kilowatts of the electrical machine. And we're sort of running, this is not, the scale is not proper here, but this is essentially outside of the NTE. So the engine was spending most of the time at a place where it's not even controlled for NOx. It's not even designed for low NOx. So that's what's happening. Once you correct for that, so you do the right matching of the engine and the hybrid system and the controls, things improve. So because we had this big issue, by the way, California had suspended at some point issuing hybrid permits to our competitors because they could not fix this problem. But we took a Coca-Cola delivery truck, and instead of Coca-Cola, it was hauling essentially a full-blown emissions measurement system with dilution tower and everything in it. So in the trailer, in that picture, there's actually a full-blown emissions lab. And with the right matching of the engine, the right derating of the engine for the hybrid system, you can see on the graph in the middle, you can see NOx and CO2. Now this is well, kind of real-world emissions. It is on a this is measured on a chassis dyno, but the drive cycles were real California drive cycles that were fed to the chassis dyno. And then you can see the drop in both CO2 and the movement to the left, which is the reduction in NOx that comes with actually burning less fuel, but with your after-treatment system doing the same job. So it's working properly on less fuel burn. You will expect less NOx to come out of the tailpipe, which is kind of what we showed. But then that made us think about what is the proper way of doing hybrids. So our system and all the commercially viable systems today are so-called P2 hybrids, which means that the electrical machine sits in front of the gearbox so that the electrical motor torque gets multiplied by the gearbox. And that's great because you can use a relatively low torque machine and have all the advantages of a gearbox. The problem is that now the gearbox is, you have a fight there for torque capacity between the electrical machine and the diesel engine. And typically, the front end of the gearbox is actually the torque limitation on the powertrain. And that's exactly, so you're trying to put torque, combine two torques, let them fight for limited torque capacity in the rest of the drivetrain. Plus, if you put the machine in a P2 position or a P1 position, which some people call it integrator starter generator, so if it sits on the flywheel of the engine, then you also see all the torque interrupts of AMTs, of automated mechanical transmissions. Now, another popular choice is to put the motor on the back of the transmission, and that's called a P3, or if you put it in the axle, it's called a P4 hybrid. And all the benefits of the P2 go away and become disadvantages of the P3. So you don't have more ratios now. Torque that you get out of the electric motor, that's the torque that goes to the wheels. But you do have a big advantage, which is you're not fighting for torque capacity. You can put enormous amounts of torque. You're only prop shaft limited at this point. And it's also very simple to do it as an aftermarket arrangement. So a lot of launch assist systems, electrical or hydraulic, are of this characteristic. They also don't care about torque interrupts. In fact, if you have an AMT in this P3 arrangement, you can fill in the torque interrupts. So while the transmission is shifting and the engine's moving up and down, you can use the electrical torque to still send power to the wheels. And we thought for a very long time that you actually have to choose between the two. It turns out that you actually don't have to choose. And so we built such a transmission. It only has one motor, but you can connect it selectively to the front or the back. And we're not the only ones doing this, but I think we're probably one of the few people with transmission experience that does it. And then you can see the results here. So the orange bars are the improvement of a normal P2, of our first generation P2 architecture. The blue and the green are two different torque ratings of the electrical motor when it is in this switchable P2, P3 position. So without adding cost, but adding complexity in the controls, no doubt, but without really adding cost, you can improve the fuel savings. So therefore, you improve the, keep the cost, which is the denominator, of the value proposition constant, increase the fuel savings, which is the numerator of the value proposition. So now you're affecting the value prop better in a positive direction. So we think that's a solution for medium-duty trucks, but for cities, it comes into the EVs. And our claim is, in spite of the fact that EVs are very popular in direct drive, no transmission, no gearbox, just a direct drive electric motor, that works very well for pass cars. Really well, really smooth, really easy to control. But for things like city bus, not really. And that's because you really need low gears to be able to start a heavy vehicle on a hill without having it roll backwards. And you need higher gears so that you can run the motor efficiently. The electric motor efficiency map is, of course, different than the map of a diesel engine, but it still has its high efficiency points in the 95% efficiency range, and its inefficient points in the 75 to 80% efficiency. So if you're running the motor in an inefficient mode, that means that you're limiting the range, or you have to increase battery storage, or all those things. So this scheme here is trying to illustrate the difference between a direct drive and a 2-gearbox. That product is actually now sold in the US with Proterra buses. It's manufactured in Europe, and it's being tried here in Europe. If you have only one gear, there's a strict relationship between the vehicle speed and the motor speed, which means that there's only one particular regime of that bus where you are in the 90% and over efficiency range, and at some parts of your cycle you're going to be inefficient. If you put 2 gears, you're spending more time in the 90+% efficiency, so you're getting the same torque to the wheels, you're getting about a 10% improvement in efficiency, and a 2.5 times better gradability. So with a direct drive electric motor on a heavy bus, you can barely do a 10% grade. In China, you need to be able to do, I think it's 18 or 20, something like that, around 20% grade just to get homologated, right? So, and that does happen once you use your first gear. But the effect of reducing the torque in the motor also means that the direct drive motor that Proterra was using was 380 kilograms. Now the motor and the transmission together are 177 kilograms. The other piece that has changed was that they either had in direct drive a normal axle, but then could not climb grades, or they had a very high number axle, which is heavy and expensive and tailor-made. In this piece, they went to a axle with a ratio 9, almost 10 ratio, still high. So then we're working with the Department of Energy to do 4-speed transmissions here. And again, I won't go through the numbers, but now when you're looking at the efficiency improvements over the 2-speed, you're seeing something between 12 and 17%. Compounded with the initial wins, that's around 25% better efficiency than a single motor, which is what most people do today. That means a 25% increase in range, or the potential to chop off 25% of the batteries, which is the big cost of these buses. Gradability still improves. The other piece, which is hidden here, you cannot see it, but the axle ratio went from 9.8, which is still a special axle, very heavy, very expensive, to a 6.2 axle, which is an off-the-shelf, normal commercial vehicle axle. So, in conclusion, 2024 looks like a watershed year, at least in the US. We have all indications that this is not so far off for what's going to happen in Europe, given the European Commission stance on CO2, as well as what we've heard that is happening from municipalities and so forth in terms of NOx. This is a big deal because simultaneous CO2 and NOx reductions are hard, and that they need new engine platforms, essentially. Long haul, we'll wait and see what Tesla has to show in September, but the long haul electrical truck does not seem to be within reach, either battery-driven or fuel cell-driven or micro-turbine or whatever-driven, not even a serious hybrid, and it's just an efficiency game in the transmission and the engine that's being played there. But 48-volt and mild hybrid absolutely makes sense. Once you have more than 10, 15 kilowatt of electrical power on board, there are wonders that you can do on the engine side. You can do electric boosting, you can do electric valve actuation, and all these goodies. The P2, P3 hybrid, the integrated hybrids do offer a substantial benefit in terms of the ability to tailor it to the application and maximize the return per application, which has always been the Achilles heels of hybrids in the commercial vehicles. But the EVs are really coming up fast, enabled especially by not just 2-speed, but maybe 3 or 4-speed transmissions, because that is a great ability which is needed for the application, but also a battery range or battery capacity game. So with that, thank you.
Yep, thank you very much. Are there any questions for Mihai? Okay, just one from me then. You've explained, but I just want to make sure I got it right. Your 2024 breakpoint for the introduction of these technologies, are they somehow related to the second stage of greenhouse gas phase 2 in the US?
Exactly that.
That was driving.
So our hope, certainly our expectation until November 8th of last year, was that the additional NOx requirements driven by California will be actually put in practice by the EPA, and the EPA would have made them to coincide with January 1st, 2024, so that it would give the engine manufacturers enough time and fewer shocks, even if that one shock would be stronger, but fewer shocks to go through. Now, as far as NOx is concerned, things are a little bit floating. There is this now clear possibility that California will go and do it by itself. And then the hope is that CARB will be rational and sync it with the EPA greenhouse gas step, but there aren't any sort of guarantees.
Okay, and do you think that if, let's say, greenhouse gas phase 2 goes ahead as planned, new technologies come into play in the US in 2024, do you think those technologies would enter the European market at the same time, even if the set of legislation would not be requiring those technologies to come?
Yeah, so we're speculating now, but we have to look at the US engine market and the European engine market are pretty much tied to the hip. You have Cummins is by far the biggest manufacturer of engines, heavy-duty highway engines in the US, and they're trying to grow into Europe. They're coming up with new technologies. I have a hard time believing that they will not use that as a competitive edge to come into Europe. Then the next ones are Daimler and PACCAR, who are essentially trying to use European engines or European cousins in the US. And then the third one is Volvo. Even the last one, Navistar now, is in this consortium with Scania and MAN. So it's very it seems that all the cards are pointing to joint technologies.
Okay, excellent. Great. So thank you very much again, Mihai, and we'll move to the next presentation. Thank you.
Thank you.